Hi, my name is Parker Kelly, and this is my design project report. My my group members were Hannah, Edward, Pedro, and Ashley, and what I mainly worked on for this time around was all of the flex, as well as some of the report. For our problem description, we were tasked with designing a piezo thermal resonator cantilever to maximize tip displacement for a fixed large first mode quality factor. The materials we decided to use for our cantilever was the barium titanate for our piezoelectric, and then aluminum for the metal around it. As you can see here, we had some dimensional constraints, but the only one with a range was the thickness of the aluminum, because that is what we wanted to optimize for. It was the thickness on the top and the bottom. Here are the property constraints as well as stiffness matrices that we used for our materials. This is our design as shown in like a diagram, and our external factors applying on the cantilever was the electric field as well as our thermal energies coming from heat from internal generation as well as heat from convection. The additional client requests we had was to get the tip displacement at thermal equilibrium, which we had our optimizing for our max displacement at thermal equilibrium, so they were both the same, and then our time when we were at 90% at thermal equilibrium. We decided to simulate in 2D, as well as we ran an additional projection, which we got to be 0.425 micrometers of displacement. Looking at analysis, our first two equations here are for our heat equations, with the first one being heat flux and the second one being heat flux with convection included. We also then see our electric field equations with electric field with Gauss law subbed in to get the strain when simplified. And this all goes down to our overall stress and strain, which can be subbed into our curvature equation right here. This curvature equation can then be further taken down into our displacement of the tip equation, which is just half of the curvature times length squared. That equation, when applied to module analysis, would have to become a different linear set of differential operators, which can then be sorted through to get our final to our final one here, which is the angular frequency, so we can solve with modular analysis. For implementation, all the red code is what we changed, except we missed out some of the matrices down here. They are changed for our values. For validating the model, we used equation to test the theory against our own, and we were close. We were within what we assumed would be the difference, because our simulation included heat and the theory did not. We also tried it at a bigger size, and they were within the proportion we thought they would be. We checked the electric field lines to make sure that was working properly, as well as the heat lines to make sure they were working properly, as well as we ran it under module analysis to make sure that it did actually resonate, which it did. For scripting, this is our code that we use to convert our flex out to the Python. For optimization, we used a grid search, which sets upper and lower bounds, goes through those bounds at set interval, and makes a grid that it searches through and takes the max values. After our grid search, we then move to gradient ascent, which goes through iterations over the peak, and it reduces that interval over that peak over time until it gets the smallest value, gets the most close to the peak it can, and this was our final output. Which showed our tip displacement was maximized at the highest bottom thickness and lowest top thickness. We concluded with a maximized value of displacement of 15.8 micrometers, with the top layer of aluminum being 5.1 micrometers and the bottom layer being 4 micrometers. At time for 90% of thermal equilibrium with voltage affecting it was found to be 20,700 seconds. Our considerations for this were the size scaling, which could affect it, as well as the resonance not being directly applied, and as well as outside heat can be in consideration when taking outside of the simulation. We also used a 2D simulation, which can have can be different from 3D simulations in real life. Our confidence was good, except that we didn't have a resonance and voltage and heat mix, as well as our material properties could be slightly off. Our limitations, we assumed linear relationship and assumed isotropy.